today, our first speaker will be Adrian Lupascu, who's a professor at the Institute for Quantum Computing and the University of Waterloo here. And he will be talking about the demonstration of switchable detector-field coupling implemented using superconducting systems. And you will have 25 minutes, and when we are 5 minutes to the end, I will give you a warning. So the floor is yours, Adrian. You can start.
Thank you, Adam, for the introduction. And I would like to start by thanking the organizers for the invitation. It's a great pleasure to be here and have the opportunity to present this work. So our work is motivated by entanglement harvesting, and in Rob Mann's introduction and historical overview on Monday, we saw that entanglement harvesting is one of the main topics of research in RQI, and we believe that its validation would be a very important milestone for the field with the potential to open new research avenues. So thinking about this topic from the perspective of experimentalists, we get to realize that the experimental challenges are daunting. One is to control the interaction between each atom and the field, with the strength ranging from complete decoupling, so from zero strength all the way to very strong coupling. This change in the interaction strength has to be made very fast. And then there are also other implicit criteria, such as the need to have negligible intrinsic decoherence, and in particular some very hard criteria for readouts. So the readout needs to be high fidelity, and an even harder, and depending on your point of view, important requirement could be that the readout or the detection is locality loophole free. Already more than 10 years ago, it was recognized that superconducting systems are a promising candidate to explore entanglement harvesting in the lab based on some unique properties that they have. So these are two proposals, one on space-like separation events leading to entanglement, and another proposal on past-future entanglement. So this is the outline of my presentation. I'm going to start with a very brief introduction to superconducting circuits, enough to bring in some important concepts, and then I'll give an overview of progress made over actually around 10 years in the field that is leading into some of these experimental requirements for entanglement harvesting. I'll talk primarily about strong atom-field coupling, but also say a bit about fast control of atoms. And then I will talk about our recent results on the demonstration of a switchable atom-field coupler. And then I will close with a discussion of recent work that we did towards the implementation of entanglement harvesting setup, and go over some challenges and open questions. So superconducting qubits all rely on the magic of the Josephson effect. So the Josephson effect essentially is about the dissipationless flow of current between two superconductors separated by a tunnel barrier. So this is the tunnel barrier here, and the two superconductors are called left and right. There is a surprisingly simple low energy theory for this system, which essentially amounts to considering two components. So such a system can be described with a simple Hamiltonian, where one part is essentially hopping of Cooper pairs from one side to another. So this is coherent transport of Cooper pairs where one Cooper pair can hop from left to right or right to left. The other component to the Hamiltonian is a charging energy component, where essentially the charge imbalance between the two sides, between the two superconductors, leads to an electric field, which leads to then an electrostatic energy. And finally, one last ingredient is that when you place one or more of these Josephson junctions in a loop, you need to consider the role of the magnetic field. And there is a complex factor appearing in this hopping term, which is akin to an Aharonov-bound phase. So putting together Josephson junctions in different configurations, you can form an infinity of engineered or artificial quantum systems. And in fact, several tens of them are being actively explored in quantum computing. For us, the main system of interest is the so-called flux qubit, which in its original form was, or in its original sort of configuration was introduced in 1999 by Hans Moy et al. And essentially, it consists of a superconducting loop with 3 Josephson junctions. So from here onwards, you'll see these cross-like symbols which represent the Josephson junctions. With an applied magnetic flux, which is needed in order to make it work. In real, the way this circuit looks like is this micrometer-sized loop made of aluminum, where the Josephson junctions are these overlap areas here between 2 aluminum layers. So you can put together a Hamiltonian based on rules, and they involve the type of tunneling and electric energy, electrostatic energy components that I showed earlier. And when you do this calculation, you can find the spectrum of the system. And for a typical flux qubit, the energy levels as a function of the applied magnetic flux look like this. The transition frequencies are in the gigahertz range. So these are microwave frequencies that we need to consider. And the very interesting feature of the flux qubit is the high harmonicity, namely around this half a flux quantum point, which is a symmetry point for the Hamiltonian. You find that the energy level splitting between the ground and first excited state is very different from the other energy level splittings, and therefore you can take this to be a 2-level system to a very good approximation. So in this model, the Hamiltonian is given in this form, which is essentially Hamiltonian expressed in a basis formed by 2 states where you have dissipationless currents flowing counterclockwise or clockwise in this ring, and you have a term that corresponds to tunneling between those 2 states, and another term that corresponds to an energy imbalance between those 2 states, which is controlled by this applied magnetic field. So this energy imbalance is 0 at half a flux quantum. In the field of superconducting devices, light-matter interaction has been a central topic, standing on its own as something of fundamental interest, but also being highly relevant for quantum information processing. And the most simple setting to look at light-matter interaction is the coupling between a 2-level system and the harmonic oscillator. This is described by the James Cummings Hamiltonian, which has the atomic Hamiltonian, the bosonic mode Hamiltonian, and then a bilinear coupling between those 2. The most basic manifestation of this coupling is the coherent energy exchange between for an excitation between the qubit and resonator, and this occurs at the coupling rate G, which is the strength of this interaction. And for a very long time, an important milestone in the field of quantum optics, and not in superconducting devices, but in, say, regular atomic physics, has been to attain the strong coupling regime, where this coupling strength is much larger than the decoherence rates of the subsystems involved. So this took a couple of decades in quantum optics to be realized. And looking at the field of superconducting circuits, an interesting question emerged on how strong this interaction can be made. And a detailed discussion of this point was presented in this paper from 2007 by Devoret et al., where essentially the comparison between atomic physics systems and superconducting circuits was considered. And essentially, the 3 configurations that were compared here were having a Rydberg atom. So this is a regular atom in a highly excited state coupled to a 3-dimensional resonator. Then having a superconducting qubit with charge-like coupling, and then a superconducting qubit coupled to the current in a resonator. So one very intriguing result that emerged from this analysis was the fact that in all 3 cases, the normalized coupling strength, so this is the coupling strength divided by the transition frequency, is actually dependent on the fine structure constant alpha. This is something that you wouldn't immediately expect when you think of these engineered quantum systems, but it is actually something that kind of underlines the fundamental limitations of the physics. And as you can see, as you move from real atoms to artificial atoms in different configurations, you find a more and more favorable scaling with alpha. So with alpha being of the order of 1%, we actually expect here that this normalized coupling strength can be of the order of unity or even higher. So I'm not going through some details here, but just to clarify this, all of these factors here are of the order of unity. So in the end, this alpha power minus a half can lead to this being a fairly large number. And the first experiments that explored the possibility of reaching strong coupling were done more than a decade ago, looking at single qubits coupled to resonator mode. And about 5 years ago, there was another experiment where this coupling strength was even made to be comparable to the transition frequency of the atom and the resonator. So let me now talk about a different setting for light-matter interaction, which is now coming close to what is of interest here, namely the coupling of an atom to a one-dimensional field. So this can be realized in many ways, but here we are thinking about an artificial atom coupled to the electromagnetic field in a superconducting transmission line. And the Hamiltonian for the system is this Hamiltonian where we have the atomic Hamiltonian, then a set of bosonic modes corresponding to the transmission line. The sum here is shown as discrete, but it reaches a continuous limit when this transmission line has infinite length. And then the two-level system is coupled to each mode. So here the A, K dagger and AK are creation and annihilation operators. G is the coupling strength, and UK are mode factors. So this is an important system in quantum optics. It forms the basis of quantum networks. And another interesting angle here is that in a different context, this is called the spin boson model. It was investigated very actively in the field of condensed matter physics, and it has this feature that as an open quantum system, so open from the point of view of the atom, depending on this coupling strength alpha here, you can observe a transition from coherent to incoherent behavior and all the way to localization. So, so for this system, the strong coupling regime, which is essentially is the situation where the emission rate of the atom into the waveguide dominates other non-radiative decoherence channels, is important because it means essentially that you can have coherent exchange between information in atoms and the field. And this was again explored in atomic physics. And in superconducting devices, it was this regime was demonstrated for the first time in 2010. And then there are other experiments that look at different aspects of this physics, such as using this for photon sources or looking at interaction between two atoms mediated by the field. About 5 years ago, together with our collaborators, we worked on an experiment where we designed a coupler between a flux qubit and the transmission line, which implemented a new regime, the ultrastrong coupling, where essentially the coupling strength is so high that the emission rate becomes comparable to the atomic frequency. And this is fundamentally interesting because it is something intriguing in terms of the conceptual basis for understanding light matter interaction, and it opens new avenues relevant for entanglement harvesting in particular. So after having gone through some of these results over about a decade on light matter interactions and strong coupling, I just want to mention briefly another important ingredient in this work towards entanglement harvesting, which is about controlling an artificial atom very fast. And this is This is a result from an experiment we did in 2015, where we took again a flux qubit with a transition frequency of about 2 gigahertz, and we applied resonant pulses, which were defined to have very precisely controlled shapes. So when you look at this signal here, this is actually an electrical signal with a frequency that corresponds to transition frequency, and we very carefully control rise and fall of this envelope. So now, normally such a pulse induces Rabi oscillations, which is what we observe. So these are oscillations between the ground and the excited state of the atom. But when we make the pulses very strong and short, we see that the role of the rise and fall times is important. And this calls for a different framework to describe the physics here, which is Floquet dynamics. And essentially this experiment, besides exploring this physics, also provided some evidence that we can control these pulses with a precision at the level of 0.1 nanoseconds, so way below the inverse transition frequency of the system. So this completes my overview. I wanted to convey this point that this topic has been running has been active in the field for a long time. I want to move on to the main topic of my talk, which is the demonstration of switchable coupling. So this is about implementing a coupler between an artificial atom and the electromagnetic field with a control strength. And the relevance of this was recognized again more than a decade ago. There was a proposal by Pero Padre et al. Where several configurations for using essentially flux qubits or variants of flux qubits to implement the switchable coupler were explored. A similar type of superconducting device was also used in proposals on entanglement harvesting by Sabine et al. And essentially, we were inspired by these proposals and developed a somewhat different circuit, which from the perspective of an experimental, has some advantages with regards to simplicity and how easy it is actually to implement in the lab. So our design essentially relies on, is inspired by an idea from coupling of two superconducting qubits, where a setup as illustrated here was used, where essentially have qubit 1 and qubit 2, and in between there is another system which in a sense is a qubit as well. And it has this property that the current through this loop in the ground state of this system changes very fast with magnetic flux. So if there is a change in current in this qubit, it results into a large change in magnetic in current in this loop, which is then seen by this other qubit. So there is an effective inductance, and what is important is that this effective inductance can be controlled by applying magnetic flux to this loop. So we took this idea and we looked at how we can use it to implement the coupler between the current in a qubit and the current in a transmission line, which is essentially coupling to the momentum of the electromagnetic field. And the final circuit looks like this here. So you have two loops. One is the proper qubit loop, and the other loop is essentially this control loop, which achieves tunable coupling. So this is the experimental device. The core of the system is this circuit with a qubit loop here and the coupling loop here. This is essentially made part of a transmission line, which is where the electromagnetic field resides. The magnetic flux through both of these loops can be controlled, and it can be. We haven't done this in this experiment yet, but it can be controlled very, very fast. So you can do low DC control and very fast control. So now this is part of a full chip that has here the transmission line. So this is where we have the electromagnetic field, and then there are other elements that were not used in this first experiment for reading out the state of the qubit. I want to emphasize that this experiment was enabled by a novel method to implement air bridges in superconducting circuits. So these are these tiny wires that you see here that connect ground planes. I will not go into the details, but these are actually essential for making all of this work. And essentially, the setup used in this first experiment was to probe the transmission through the qubits. So they send microwave continuous wave signals, and they look at the coherent transmission. And the results look typically like this. So when you sweep the two currents controlling the fluxes in the two lines, we see features which correspond, roughly speaking, to resonance of the qubits and the applied frequency. And now we have to do some work on crosstalk calibration to bring out what the actual fluxes are applied to those two loops. And when we do this, we see the kind of features we were expecting, where essentially there is suppressed transmission over a line here, which depends on the applied magnetic flux to the qubit loop. And by extracting these points of suppressed transmission versus the two control fluxes, we can compare this with the full quantum circuit model, which is fairly complex at this stage with several junctions involved, and we are very happy to see that there is excellent agreement with this model. So now looking at the shape of this transmission curve, so this shape is a Lorentzian, and its width and suppression on resonance give a wealth of information on the coupling of the system to the field, but also on intrinsic coherence rates and temperature. And I wouldn't have time to go over all of these details here, but to focus on the main result, essentially we can extract the transition frequency of the two-level system. Excuse me?
That's 5 minutes to the end.
Okay, thank you. So we can extract the transition frequency at the qubit symmetry point versus this control flux f beta. So this is again important validation for the circuit model, but most importantly, we can measure the emission rate gamma 1 into the waveguide as a function of this control parameter. And what we find is that our experimental points range between 10 to the minus 2 and several gigahertz, so they span 3 orders of magnitude. And this is a comparison with our theoretical model. And we see fairly good agreement over a broad range of applied control fluxes, with some disagreement, a large coupling that we are still trying to understand better. But here we believe some experimental limitations came into play. So this essentially establishes this result that we have built a tunable coupler between an artificial atom and the electromagnetic field. And the coupling ranges effectively from 0 to a coupling strength which nears the ultra-strong coupling regime. So we would like this coupling to get even larger. And again, with improvements in design, we are confident we can get there. Now in the final part of my talk, let me say just a bit about our work towards implementation of entanglement harvesting. So now we take the device we developed and demonstrated this experiment, but we bring together two qubits. Each of them is coupled to the same transmission line. So this is this long meandering line here. So with this chip size being several millimeters, this long meandering line is essentially such that we can create an effective separation between the qubits that is of the order of 10 centimeters. These are some close-ups around the qubit region, which essentially look like what you've seen in the previous setup. So it is the same unit, but just two of these qubits are brought together. This is how this device looks like in real life. So it's placed here on a sample holder, ready for an experiment. And this is another picture showing some more details here. And yeah, we have started an experiment using this first device. We've seen, for example, that the flux detectors are working well, so they respond to magnetic flux, and everything looks all right with those, but had some initial problems with the qubits, which we are working on fixing. And yeah, essentially, this is now coming together, and I wanted to close with a brief discussion of some challenges and some open questions in this as we are building up this experiment. So firstly, we've done some theory work in collaboration with Eduardo Martinez, where we can look at the effect of the field temperature on entanglement harvesting. And we find that actually the temperature is quite critical and needs to be effectively very low in order to generate entanglement, which essentially is pushing some limits on design and control speed. The other challenge is that the amounts of entanglement, even with ultra-strong coupling, are very small. So we need to design detectors that have high fidelity and low drift, which again is something that we are starting to put together, but we'll have to go through the process of characterizing this. And the final point, which is quite interesting for me, is that we still need to consider that the switching interaction model is an idealization, and we need to do some work to look at the qubit coupler as a single system and introduce a more operational definition of entanglement generation. So this, let me summarize, where I covered an overview of strong coupling and fast control work over a decade, essentially in the field, and then I described our recent work on demonstration of switchable coupling. We want to do future work on understanding better realistic, so kind of device physics aspects that are important for this experiment, and we hope that with further experimental developments, we can develop and looking at the relevant physics, we can bring entanglement harvesting to the lab soon. Let me just take a minute. I think I'm at time. If I can take just a minute to tell you a bit about our team. So I want to say that I'm really fortunate to work with a great group of people who put all of this together. And firstly, I wanted to mention the role of Noah Jansen. So most of this work was essentially the result of his master thesis. So not only did he implement this coupler, but also in the process, he came up with a novel fabrication technique for the field, which has an impact way beyond the results presented here. Shidai is a senior graduate, a PhD student who's done a lot of work on modeling the circuit. So he's an expert at flux crosstalk, device physics, and so on. So he analyzed lots of this data and developed actually extension to known models for understanding this. Sean Ren did work on these simulations looking at entanglement harvesting, but also on the experiment itself, on the control and so on. During his master thesis, Jahawashi worked out the model for the detector during the master thesis that was completed a few years ago. And then newer group members, Lucas Hack is a master student who works on the entanglement harvesting experiment, and Michael Tyne and Lena Kornick are undergraduate students who contributed to the recent experiments. And also want to say briefly that I'm very happy that we can discuss many of these ideas at UW with Eduardo in particular, but also we are benefiting from a very inspiring environment with several groups engaged in RQI. And finally, let me acknowledge our sponsors. Thank you.
Thank you, Adrian, for your talk. We'll have time only for one question. So, Masahiro, you can go ahead.
Thank you very much for very impressive experimental talk. Very nice. And I have a question. So if you succeed in extraction of entanglement from vacuum, that is entanglement harvesting, but you said it may be very weak entanglement. But if you provide some entanglement distillation protocol in your lab, then we may have strong Bell pairs like that. So do you have such a plan?
Yes, this is a great point. So indeed, the amount of entanglements for each cycle would be really small, even with the strongest coupling that we can use. And there are some interesting theory questions around what happens in that strong coupling regime. But I think that in principle, one can imagine expanding this setup to include entanglement purification protocols. So I think by taking essentially several of these qubits and going through cycles where gradually we reset some of these qubits and couple them back to the field and so on, there is you can imagine doing this, and of course the point is that everything scales up in terms of difficulty, but there is a path. I think this platform I would say is probably one of the most promising to implement things of this sort due to the flexibility you have in designing the circuits. So, yeah. But this is probably many years away.
Thank you very much.
Thank you.
So, thanks. There will be more questions on the end. So if you can, Adrian, stay, it would be nice.
Sounds good. Yeah. Thank you.
Good. And thanks again for your talk.